Okay, welcome to the second part of our lesson. What we have done is, in the first part, we talk about what we call statement questions, then descriptive questions, and we have seen how to answer them using suitable examples. Now, we are going to talk about comparative questions, where you have to show a contrast. This is like this, that is like that. And use words like while, but, whereas. Sometimes we have a table on one side is this fact, on the other side is the other fact. But the points we give on this side and on the other side have to be contradictory. Sometimes you may be asked to compare and contrast. If you're comparing and contrasting, you first list what is similar amongst them and then what is different amongst them. So for example, in the question you have here, distinguish between transverse and longitudinal waves, giving examples. In our study, we talk about waves. Waves is a transmission of a disturbance through a medium. The medium may be a material medium like air, water, and so forth, or it can be an immaterial medium, of course that is a vacuum. Electromagnetic waves can be transmitted through a vacuum very well, but it's transmitted through a medium. So, given that we have broadly speaking, we have two types of waves. What we call mechanical waves, which must be transmitted through a material medium, and electromagnetic waves, which can be transmitted through a vacuum or immaterial medium. Electromagnetic waves are the forms of light. Radio waves, microwave, infrared, visible light, X-rays, gamma rays, ultraviolet rays, all that. But the mechanical waves exist also in two forms, either transverse waves or longitudinal waves. And here they want to give an example. Now, a transverse wave, a good example of a transverse wave is water waves in the beach, the sea, or in a container, and it's made to move. So it moves up and down, up and down. That's how it appears to be moving through the medium. So in actual fact, the wave is moving from one point to the other like that. But the medium through which it is moving is such that the particles of the medium are displaced up and down, up and down, up and down. They are displaced in such a way that it is perpendicular to wave motion. So, in that case, would you say that the particle's displacement is perpendicular to the direction of wave motion? That is true for transverse waves. Good example, of course, is the water wave. While when it comes to longitudinal waves, in the case of longitudinal wave, a good example of that is sound wave. These ones are transmitted in such a way that there is compression and rarefaction. Compression and rarefaction. Compression and rarefaction. Okay? Compression, rarefaction. Compression, rarefaction. What this means is simple. That like sound occurs because of vibration, sound from human beings because of vibration of what we call the voice box, moving up and down like that. Okay? So because of the compression and rarefaction, sound is transmitted like that. The particles of air are compressed, then they are a bit freed. Compressed, then a bit freed. Compressed, then a bit freed. And that's how sound is transmitted from the source to the receiver. So in this case, I have given my answer as, in form of a composition. I have given the examples and I have given the difference in the manner in which transmission occurs or formation occurs of the transverse wave and longitudinal wave. And that's what we mean by comparative questions. This is like this, while the other one is like that. let's go to the numerical question. Now here, that's where I'm going to write on the board, as well as the last question. A manometer containing water shows a difference in level of 10 centimeters when connected to a laboratory gas supply. Calculate the pressure exerted by the gas supply. And you're told to take atmospheric pressure to be 100,000 Newton per meter squared. That's what the symbol means. So in this case, we basically have a situation like that. Gas is coming in. The liquid level is initially at the same point. Then, because this gas is coming in and exerting pressure at this point, the level here will be slightly lower, while the level here will be forced to rise slightly. If the difference is 10 centimeters, like the question is saying, the level here will be lowered by 5 centimeters, while the level here will rise by 5 centimeters, so that eventually the difference is 10 centimeters. So the liquid level here will be there, while this is 5 centimeters, so the liquid level will be there. And that is that. Because this side of the manometer, U-shaped tube, is open, that means there is pressure here due to atmosphere, we call that P naught. So there's pressure here due to the gas. But at the same time, at this point where there's a difference, there's pressure due to the water, because it was water which is being used in this liquid. So, how do you find the pressure of the gas? It should be equal to the pressure of the atmosphere and the pressure of the water, because that's where it is at the same level. The pressure of the gas acts to this point, while for water and atmosphere is that way. So, pressure of the gas is pressure of the atmosphere plus pressure of water, or do the water polar. And that is pressure of the atmosphere plus rho of water, h of water times gravity, rho hg. That's how we find pressure in terms of liquid. Then we substitute the facts that we already have here. That means this will be 100,000. Density of water will be 1,000. Height of water will be 10 over 100, while gravity shall be 10. So gravity is a constant, 10 newtons per kilogram. Height is 10 centimeters, we divide by 100, 10 meters, while the density of water is 1,000. So what happens here? We do our cancellation, we get it to be 100,000 plus 1,000. And your answer is 101,000 Newton per meter square. That now becomes the density of the pressure due to the gas. The pressure due to the gas. Mathematical question. Get the formula. Identify the values given, like density was given, this for water, it should be that, or this is known. Height was given, and gravity is a constant, it's known. Pressure of the gas of the atmosphere was given. Work it out, and you get your answer like that. Then finally, we come to the graphical questions. Describe Hooke's law and illustrate using a graph. Like we say, Hooke's law means you have force and you have extension. Force causes extension. So force is the independent variable. It should be on the x-axis. Extension is a dependent variable. It should be on the y-axis. Unless otherwise it is specified, put force on the y-axis, extension on the x-axis. So it should be like that. Extension maybe in centimeters, force maybe in newtons. So we have this. No, zero force, zero extension. Some force, some extension. Some force, some extension. Some force, some extension. You end up having, that kind of line up to a point where it begins to go off. This point is what we call the elastic limit. Point beyond which any force acting on the spring will cause an extension which is irregular from before. Otherwise, Hooke's law is obeyed. So we have looked at what we mean by statement questions with examples. We have looked at descriptive questions with one example. We have looked at comparative questions with one example, numerical questions with one example, and finally, graphical question with one example. Anytime you get these kind of questions in your physics assessment, I'm sure you will do very well. All the best. See you next time.